Somewhere out there right now, a black hole with the mass of 10 million suns is moving through a galaxy at nearly 1,000 miles a second. And nothing in that galaxy is fast enough to get out of its way. It isn't sitting quietly at the center where black holes are supposed to stay. It's running. And the James Webb Space Telescope just caught the trail it left behind, a glowing wound across an entire galaxy, 200,000 light years long. Stick around because I'm about to walk you through what scientists just confirmed about runaway black holes and why the idea that one could be heading toward us isn't science fiction anymore. It's on the record. And if you want more real space discoveries broken down without the exaggeration, hit subscribe now because this is final proof. And this is one of the strangest things anyone has pointed a telescope at in years. Let's start with the assumption this discovery just broke. For most of the history of astronomy, black holes were treated as anchors, fixed points, the thing every galaxy is built around, sitting dead center, patient, unmoving, waiting for gas and stars to fall into it. That's the picture in almost every textbook illustration you've ever seen, a galaxy spinning gracefully around a black hole that never goes anywhere. It turns out that picture was only ever true some of the time, and the exceptions to it are far stranger and far faster than anyone expected. To understand how we got here, you have to go back to 1963 to a New Zealand mathematician named Roy Kerr. Kerr was working on Einstein's equations of general relativity, trying to solve one of the hardest problems in the field, describing what a spinning black hole actually looks like mathematically. He succeeded, and what came out of that solution reshaped how physicists thought about these objects completely. Kerr's math produced what's now called the no-hair theorem, the idea that a black hole can be fully described using only three numbers: its mass, its spin, and its electric charge. Strip away everything else and that's all a black hole is, mathematically speaking, three numbers. But Kerr's solution held a second, stranger implication buried inside it. Because of Einstein's famous equation linking energy and mass, and because of how Kerr described rotation, his math implied that a spinning black hole could carry as much as 29% of its total mass in the form of pure rotational energy. Spin energy, a colossal reservoir of it, locked inside the black hole like a battery that had never been touched. In 1969, the English physicist Roger Penrose took that implication further. He worked out that this spin energy wasn't necessarily locked away forever. Under the right conditions, it could be extracted, released, sent outward. A black hole, Penrose realized, could act less like a bottomless pit and more like a coiled spring, mass and spin trapped inside it, capable, in theory, of being unleashed all at once. At the time, this was a purely mathematical curiosity. There was no way to observe it, no instrument built that could ever hope to catch a spinning black hole in the act of doing anything at all, let alone releasing a fraction of its own mass as raw energy. For nearly 50 years, that idea sat in physics papers, tested only on chalkboards and in the pages of journals almost nobody outside the field ever read. Then, in 2015, the LIGO and Virgo gravitational wave observatories detected something that changed everything. For the first time in human history, scientists directly measured gravitational waves, the ripples in space-time itself produced when two black holes spiral into each other and merge. And buried in that data was something remarkable, a phenomenon researchers call ringdown. When two black holes collide and become one, the newly formed black hole doesn't settle instantly. It rings like a struck bell, vibrating at frequencies tied directly to how fast it's spinning. The faster the spin, the longer the ring. And as LIGO and Virgo collected more and more of these collisions, a pattern started to emerge. Some of these merging black holes had wildly different, randomly oriented spin axes and carried enormous amounts of spin energy, exactly the kind of setup Penrose had described on paper half a century earlier. Here's where the physics gets genuinely strange. When two black holes with misaligned spins collide and merge, the collision isn't perfectly symmetric. Gravitational waves are released more strongly in one direction than in every other direction combined. And when something releases energy asymmetrically in one direction, physics demands a reaction in the opposite direction. The newly merged black hole gets kicked, like a rocket, propelled backward by its own violent birth. If the spins line up just right, that kick can send the black hole rocketing away at speeds of thousands of kilometers per second, fast enough potentially to escape its own galaxy entirely. That's the theory. And for years, it stayed theory because actually catching one of these runaway black holes in the act, watching it move, watching what it does to the galaxy around it as it travels, seemed like it might be permanently out of reach. Small, isolated black holes are almost impossible to detect directly. They don't glow, they don't announce themselves. The only realistic way to find a runaway would be to catch a big one, doing enough damage to its surroundings to leave a mark that a telescope could actually see from millions of light years away. If you're the kind of person who wants space explained clearly instead of buried under jargon, go ahead and drop a like right now. It genuinely helps this video reach more people who'd enjoy it. That's exactly what happened in 2025, and it happened more than once. The first case, and the one that made the biggest impact, comes from a team led by Yale astronomer Peter Van Dokkum. Using imaging from the James Webb Space Telescope, his team found a distant galaxy with something attached to it that shouldn't have been there. A bright, straight streak cutting through the galaxy 200,000 light years long. To put that in perspective, that's roughly twice the diameter of our entire Milky Way galaxy, stretched out in a single glowing line. The streak showed exactly the kind of pressure signature you'd expect from a massive object physically plowing through gas as it moves, compressing everything in its path, the same way a jet leaves a contrail by compressing and condensing the air behind it. Except this contrail wasn't made of ice crystals. It was made of newly forming stars, triggered into existence by the shockwave of something enormous, tearing through the galaxy at speed. Based on the physics of the trail, researchers calculated the object responsible has a mass around 10 million times that of our Sun, and it's moving at close to 1,000 kilometers per second, not orbiting anything, not curving gracefully around the galactic center the way stars do, moving in a straight line like it was fired from a gun. The second case is just as strange, and it comes from a galaxy far closer to home, one you can actually see in a backyard telescope on a clear night. NGC 3627, a spiral galaxy roughly 35 million light years away. Researchers studying it found another long, straight contrail, this one about 25,000 light years long, cutting across the galaxy's disk. The physics pointed to a black hole with a mass around 2 million times the Sun's, moving at roughly 300 kilometers per second. Smaller than the first one, still fast enough to leave a visible wound stretched across a quarter of the galaxy's width. Two separate galaxies, two separate research teams, two long, straight, glowing scars, each one pointing back to a supermassive black hole in motion. And here's the detail that turns this from a curiosity into something genuinely unsettling. If black holes this massive are being kicked out of galactic centers and sent flying at these speeds, then the physics says smaller ones should be experiencing the exact same thing, just as often, if not more so. Gravitational wave data from LIGO and Virgo already tells us that plenty of merging black hole pairs have the kind of randomly oriented, high-spin configuration needed to produce a powerful kick. Those speeds are more than fast enough for a black hole to escape not just the center of its galaxy, but the galaxy itself, and go tumbling out into the emptiness between galaxies entirely. Which means the two we've caught on camera are very likely not rare exceptions. They're just the two big enough and loud enough to leave a mark visible from tens of millions of light years away. Every smaller one, every stellar mass runaway with 10 or 20 or 50 times the mass of the Sun instead of millions of times, is completely invisible to us. No contrail, no glowing trail of star formation, no light of its own at all. Just a black hole moving through the galaxy in a straight line at a meaningful fraction of the speed of light, undetectable until it happens to pass close enough to something we can actually see get disturbed. Now picture what that would actually look like from the inside of a solar system like ours. Last year, astronomers tracked an interstellar object passing through our own solar system, a visitor from somewhere else entirely, moving at around 68 kilometers per second, a little more than double Earth's own speed around the sun. It was fast, it was newsworthy, and it was also completely harmless, because it was just a chunk of rock and ice, far too small to do anything except get studied on its way through. Now take that same idea, and instead of a comet a few miles across, imagine something with the mass of a star, or many stars combined, moving not at 68 kilometers per second, but at 3,000. A black hole doesn't reflect sunlight. It doesn't show up on a survey the way a comet does. There would be no warning streak of light crossing the sky, no early detection months in advance. The first sign anyone would get is what its gravity started doing to the outer edges of the solar system. The orbits of the icy bodies drifting out past Neptune would start to bend, subtly at first, then, unmistakably, tugged by something massive and invisible passing through the neighborhood. By the time astronomers pieced together what was happening, the thing causing it would already be leaving. To be completely clear, nobody studying this is telling you to panic, and neither am I. The odds of a runaway black hole passing anywhere near our solar system in any of our lifetimes are vanishingly small. Space is enormous, mostly empty, and the number of galaxies a stray black hole would need to cross before stumbling into our specific, unremarkable corner of the Milky Way is almost incomprehensibly large. This isn't a warning about an incoming threat. It's a description of something that is quietly, genuinely true about the universe we live in that wasn't confirmed to be true until just last year. Here's what makes this discovery matter beyond the individual black holes themselves. For decades, models of how galaxies evolve assumed that supermassive black holes stay put. That assumption fed directly into models of galaxy formation, star formation, even the large-scale structure of the universe, because a black hole sitting at the center of a galaxy interacts with its surroundings in a completely different way than one that's been launched out of that galaxy entirely, dragging gas, triggering star formation, and eventually leaving the galaxy for good, taking a meaningful chunk of mass with it. If runaway black holes are common, and the physics increasingly suggests they should be, then some fraction of galaxies out there have already lost the black hole they were originally built around and are quietly evolving without it in ways astronomers are only now starting to model correctly. There's also a deeper question sitting underneath all of this, one that connects directly back to Roger Penrose's decades-old idea about extractable spin energy. If mergers really can fling a black hole away, carrying up to a large fraction of its rotational energy converted into pure kinetic motion, that means some of the most violent events in the universe are also some of the most efficient energy conversions physics allows. A black hole merger doesn't just create a bigger black hole. Under the right spin conditions, it can turn a portion of that black hole's own mass into a rocket engine powerful enough to eject an object with the mass of millions of suns clean out of a galaxy. Nothing else in the known universe does anything remotely like that. Researchers are now actively hunting for more of these contrails, combing through Webb's deep field images and archival data from other telescopes, looking for more of those long, straight, telltale streaks of triggered star formation that only make sense if something enormous just tore through the gas at extreme speed. Every one they find adds another data point to a picture that's still being built in real time. How common are these events? How much mass do they typically carry away? How far do the smaller, invisible ones travel before finally slowing down, if they ever do? None of those questions have solid answers yet. The two confirmed contrails from 2025 are essentially the first two data points in an entirely new field of observational astronomy, one that didn't really exist as a testable, evidence-based subject until Webb's imaging made it possible to actually see the aftermath. So here's what this actually adds up to. 60 years ago, a mathematician's solution to Einstein's equations hinted that black holes could carry rocket fuel inside their own spin, energy locked away with no apparent way to release it. Penrose showed, on paper, that the release was theoretically possible. For decades, that stayed exactly there, on paper, untestable, because we had no way to observe a black hole doing anything except sitting still and pulling things toward it. Gravitational wave detectors gave us the first real evidence that violent asymmetric mergers were common enough and energetic enough to make these kicks a real physical possibility. And now, the James Webb Space Telescope has given us something nobody had before: direct photographic evidence of the aftermath. Glowing scars, hundreds of thousands of light years long, marking the paths where black holes carrying the mass of millions of suns went tearing through galaxies at speeds that make every other object we've ever tracked in space look like it's standing still. The universe was never as fixed and orderly as the diagrams made it look. Galaxies aren't just quiet spirals politely orbiting a black hole that stays where it's supposed to. Some of them are missing pieces or losing them right now in slow motion over millions of years, leaving trails that only became visible once we finally built a telescope sharp enough to see the wound. And if it happened in that galaxy Peter Van Dokkum's team studied, and it happened in NGC 3627 close enough for us to see clearly, there is no reason to assume those are the only two. They're simply the two that were big enough and loud enough and close enough for us to catch. If stories like this one, grounded in real published research instead of exaggerated headlines, are what you want more of, subscribe to Final Proof and turn on notifications. Webb is still scanning, researchers are still combing through the data for more of these contrails, and there's a real chance the next one they find is closer, bigger, or stranger than anything confirmed so far. Thanks for watching, and I'll see you in the next one.